Hi guys, in this video we will begin our look at acid-base chemistry. The handout here begins with some acid-base warm-up questions. Give you an idea of the types of questions that you should be able to answer once we go through this material. On the flip side is a acid-base reaction in which you are asked to show the complete Lewis structure of the HCl salt that is formed upon treating the free base, this compound here, which is tramadol, a drug, treating this drug with hydrochloric acid. Can you show the resulting product? Can you show the HCl salt? You might pause the video and show that if you think you can. Hopefully you can do that pretty well coming out of Gen Chem. Maybe a little review will help, but hopefully you have an idea of how to proceed here. Okay, let's take a look at the handout. Very first, very important, is to make sure you know your standard acid-base mechanism. This shows a base. Now the base is going to have a lone pair. We're doing standard Bronsted-Lowry acid-base chemistry. And then the acid. The acid is going to have a proton bonded to something else. This is shown generically as Z. There's no Z on the periodic table. Z may be a single atom, such as HCl, or it may be a number of atoms, a large covalent molecule with an H bonded to one atom of that larger molecule. Now in the mechanism, two arrows. You need to know this mechanism, what these two arrows mean. The first step of any acid-base mechanism is going to be the lone pair, and I will usually circle the lone pair. I recommend that, and I will always do it. The lone pair moves and makes bond to the acidic H. And we show that with an arrow. Lone pair makes bond to H. That's what this arrow means. I explained that here. The lone pair, the basic atom, makes covalent bond to the acidic H. The basic atom is now bonded to the H. There's that resulting covalent bond we just made. The two electrons in the covalent bond used to be a lone pair on the basic atom, but now it's a covalent bonding pair to the H nucleus. Now at the same time, that is, these two steps are concerted. At the same time, the electrons in the HZ bond break away from the H and move on to the Z atom as a lone pair. Here. So this atom, this arrow instead, this arrow moves the two electrons onto Z, and that's what leads to this lone pair being there. That's shown here. The bonding pair of electrons between H and Z move onto Z as a lone pair. Z, that is the atom originally bonded to the H, thus takes on a new lone pair. A new lone pair. Now if Z had three lone pairs here, the three lone pairs will still be there, and this becomes the fourth lone pair. The new lone pair. Standard two-arrow acid-base mechanism. These arrows, this understanding will apply to any Bronsted-Lowry acid-base mechanism. Hopefully you were taught that and you did some of that in Gen Chem. Charges. Any of the four species in the acid-base reaction may have a charge. Nothing to memorize here, just be able to recognize and determine charges. In my generic mechanism, I'm not showing any charges. Now actually, usually in most acid-base mechanisms, particularly in organic, two of the species will be charged and two of them will be neutral. That is, very often maybe the acid or the base is neutral, and then either the conjugate acid or conjugate base will be charged. That type of information I will go ahead and show you on the back side, last page, miscellaneous points to remember. You can also call this free information. Okay? And somewhere on that page or the back, I talk about charges. All right? Because here, I just make a basic comment, but I don't give you sort of the extra free information there that could come with that comment. This mechanism can be used to predict the outcome of any acid-base reaction, including back over here, tramadol. Okay? This is your HZ. Here, the chlorine is the Z atom. All right, there's a covalent bond between HCl. Where's the basic atom? We got to identify the basic atom with the lone pair. All right. There are 3 different atoms with lone pairs. Which one is the most basic? Because it's the most basic atom that's going to react as the base. And it's the most acidic proton, or the strongest acid in the mixture that's going to act as an acid. Now you know HCl is a strong acid, so that's pretty easy. You know, that's sort of in neon lights. HCl, strong acid, there's your acid. But which atom is the base? That we will need to talk about. Please recognize and use your acid-base mechanism. All right. Now during test 1, this will largely be the only mechanism. Once we get to test 2, we will have many other mechanisms, but this sets the foundation for using arrows. Okay? And I will use the abbreviation WDAM. What does this arrow mean? Well, right here I'm telling you what it means. What does that arrow mean? What does arrow mean? Well, right there. You need to know what every arrow means whenever you use one. Very important part of learning organic chemistry. Trust me. Okay. Overview of acid-base chemistry. So let's go back to some basics here. A lot of this is review. This shows an acid ionizing. There's really no base here. Of course, you have to have a base to have an acid-base reaction. Down here, I'm showing water acting as a base. We can just show this without a base. Ionization, what does this arrow mean? The electrons are moving on to A. Now here I'm showing HA. Over here I showed HZ. Either way, some books show HA, some books show HZ. Moves on to A to become a lone pair, and if this is neutral, then the A is now minus. Here the H is neutral because we can count 1 electron from the bond, but if both of these electrons move on to A, that leaves the H with no electrons, and now the H is positive. All acid-base reactions are equilibria. Can be described by Ka, concentration of products over concentration of reactants. So for this generic reaction, it would be shown like this. And the stronger acid will have a higher Ka. You should know this. I'm not going to explain all this here in this video. If you need explanation, pause it, go back, review your Gen Chem acid-base material. Now down here I show water acting as a base. Here's our acid-base mechanism. Lone pair takes H. Lone pair takes H. These electrons move on to Z. These electrons move on to A. A or Z, same thing. That lone pair came from that arrow movement, and oxygen is making a third bond to H. Now you see oxygen with 3 bonds. One lone pair is now a bonding pair, the other lone pair remains. If you do a charge, that oxygen is now positive. And so you see that we have a base conjugate acid pair, one's neutral, one's charged. Acid conjugate base pair, one's neutral, one's charged. Pretty typical. Now we mentioned Ka up here. We don't typically use Ka. Instead we use pKa, and you know the definition of pKa. It is negative log of Ka. In the end, important take home is right here. Stronger acids will have lower pKa. That's your take home. Again, mostly review. I give you 4 different types of compounds here. A strong acid with a pKa like -5, -7, somewhere down real low. Negative. Strong acids. These will completely ionize when placed in water because water will take the proton completely. Acetic acid, pKa of about 4. Not as low, so it's not as strong. Acetic acid is an example of a weak acid. It partially ionizes in water. We'll talk more about equilibria. An alcohol is going to be considered neutral, like water, pKa of about 16. Alcohols and water both have pKa's about 16. So even lower, higher pKa equals weaker acid. Hydrocarbon CHs, these are rarely, if hardly ever acidic. They're usually never acidic, really neutral, very high pKa, and most hydrocarbons have a pKa like greater than 40. So again, stronger acids will have lower pKa's. You should start learning some general pKa's for like strong acids, weak acids, neutrals, okay, as we go along. I also give you a list of pKa's in the back of your workbook. Look at the back, inside the back cover, and I give you some pKa's. For example, here's a carboxylic acid, like acetic acid. I say 4 to 5. I also give you some reasoning. Reason why. Relative compared to like the previous one. Alcohols, 16 to 17. Okay. As we go through Organic 1 and Organic 2, we'll see most of these. We'll point out most of these pKa's. And so as you go through, you'll sort of just hear these over and over, and you'll want to start sort of learning them, like a phenol. Okay, phenols, about 10. They can be more acidic. All right. All right. But importantly, what we're going to look at next is why. Why is a carboxylic acid more acidic than an alcohol? Why is a phenol more acidic than an alcohol? Questions like that. That is, how do you judge relative acidity of different molecules? That is based on 4 things. And those 4 are listed here. Now, number 1 is actually sort of a combination of 2, electronegativity and size of the A atom, when A is an atom. A, again, or Z. We'll also see the importance of inductive effects, which, by the way, we mentioned in the physical properties lecture. Need to review the definition of an inductive effect. We'll also see resonance effects and hybridization effects. Of course, if you don't know how to judge hybridization, you'll have a hard time dealing with hybridization effects. So we're starting to build. Our information builds. We use prior information to explain new things, new trends, new information. Okay, so number 1, electronegativity and size of the A when it's an atom. Let's look at this example. H2O versus HF. Which is a stronger acid? Well, importantly, anytime we ask this question, which is the strongest acid, we need to always consider the stability of the conjugate bases. I underlined that. Now you should of course be able to show conjugate bases for any acids. All right. Conjugate base of water is hydroxide. Conjugate base of HF is F minus. All right. That should be easy, but experience tells me that many of you will have issues just simply showing conjugate bases. If you're going to judge the stability of conjugate bases, you need to be able to first show the conjugate bases. If you cannot, you need to be doing some reviewing. Now we need to ask which is more stable. Okay, and the difference here, well, the answer here is the F, the fluoride, is more stable. And that's because it is more electronegative. You've got a minus on F or a minus on oxygen. Fluorine, being more electronegative, can handle the minus charge better. We can also say it likes the negative charge better because it's more electronegative. Remember your periodic trends. Electronegativity increases as you go up and to the right. So F is more electronegative than oxygen. It likes being minus. Thus it's more stable. That's why it likes being minus. It all means the same thing. So since F minus is more stable, that means HF is more willing to give up the proton, or let me say this, to act as an acid and let a base take the proton and become F minus compared to water. Now a base can take the H of water and water will become hydroxide, but water is not as eager to become hydroxide compared to HF because hydroxide is not as stable as F minus. So here's our summary there. The stability of the conjugate bases tells us which one of these is more likely to act as an acid and become the conjugate base. Next example, water versus ammonia. Conjugate bases. Well, the conjugate base of water is hydroxide, just as above. The conjugate base of ammonia is, of course, NH2 minus. And now we can ask which of these conjugate bases is more stable. Again, this is an example of electronegativity. Oxygen is more electronegative than nitrogen. Oxygen is more stable as an anion. It likes being an anion more than nitrogen does. Thus, water is more willing to act as an acid and become hydroxide compared to ammonia acting as an acid and becoming the NH2 anion. And so, in terms of most acidic, HF is the most acidic of those two, and water is most acidic of these two. What about H2O versus methane? Of course, again, conjugate base of water is hydroxide. Conjugate base of methane is CH3 minus. And which is more stable? Over here, that was more stable. That was more stable. These two, oxygen minus more stable or carbon minus? Well, again, electronegativity. Oxygen is more electronegative. It's more stable being minus compared to carbon being minus. It likes being minus more. It's more stable. And thus water is more willing to act as an acid and become the conjugate base. Thus water is a stronger acid than methane. And actually hydrocarbons, CHs, are rarely that acidic, and they're rarely more acidic than a heteroatom H. Heteroatom being like a chlorine or a nitrogen or an oxygen. Because the heteroatoms typically are more electronegative. And a more electronegative atom can bear the minus charge better. More stable as a minus compared to the carbon minus. Okay, also with one is size of the atom. Which is more acidic, HCl or HBr? Well, let's consider the conjugate bases. Cl minus versus Br minus. Which is more stable? Now, chlorine is actually more electronegative because it's above bromine in the periodic table. And you might think that that would make it more stable because thus chlorine likes being minus more. That's a reasonable argument, but it's actually wrong here. Here, size is more important. And the bromine is larger, okay? Because it's further down in the periodic table. And the valence electrons are in a more outer shell. Oh, that'd be first thing. These valence electrons are in the fourth shell, where these valence electrons are in the third shell. Fourth shell being larger. Now what we can say is these electrons are spread over a larger volume. And that actually becomes the winning argument. The size factor beats the electronegativity factor. Size of the atom is most important. Now, when going down a group, okay, straight up and down a group, now, if you start going diagonal, size and electronegativity can the difference can become more blurred. Note up here, H, oxygen versus fluorine, we went across, okay? F is more electronegative. When you're going straight up and down in a group, size, the increase in size or the difference in size is a more important factor than electronegativity. And so Br minus is more stable. Thus HBr is more willing to act as an acid and to become the conjugate base. Okay, which is more acidic, HBr or HI? Two conjugate bases. Which is more stable? The iodide is more stable because it's larger. We're in the same group. The charge is more diffuse, it's more spread over a larger atom. That's a more stabilizing factor than the increased electronegativity of the bromine. This is more stable, thus HI is more willing to act as an acid to become the more stable anion. Let's try this compound here. Question. What's the most acidic hydrogen in this molecule? Remember, it's easy if we're going sort of straight across or straight down to compare. Straight across, N and O. If this is a conjugate base, this would become N minus, okay? Just got to know that, or O minus. If these lose an H plus. Which would be more stable? O minus, because it's more electronegative. Now, let's consider the S. Which is more stable, S minus or O minus? Well, S minus, because it's larger than the O minus. So this is going to be the most stable anion you can form. Do we want to consider carbon anions? I mean, we could go back. If this carbon was an anion, I won't draw lone pairs. That's not going to be more stable than any of these. Remember, CHs are rarely acidic, especially compared to heteroatom H's. So, comparison of these three led me to know that the S minus is the most stable. So the SH compound, or the SH, not compound, but functional group, or the SH group, the thiol group, the sulfhydryl group, is the most acidic group in this molecule, because the S minus is the most stable conjugate base that we could envision. Okay, next let's look at number 2, inductive effects. And here I give you 2 alcohols. The difference being this one has a fluorine on the second carbon. Which one of these alcohols is most acidic? Now first off, we're clearly considering the OHs, because within this molecule, the OH is more acidic than the CH, the OH is more acidic than the CH. The question is really, which OH group is more acidic? We want to consider the conjugate bases, right? Here are the conjugate bases of these 2 alcohols. And let's assess the sort of the electronics here. Now the one with the fluorine has a dipole. Let's look at it first. All right. The fluorine is pulling here. Now the effect of the fluorine is felt sort of all the way through here. Kind of like tug of war. If you got someone on the end pulling the rope, someone way over here will be pulled as well. Okay? Now we'll talk about a distance effect here, but that fluorine is pulling, and so some of the electron density that's here on this oxygen anion is pulled this way, and it's being pulled away from the oxygen nucleus. Okay? Ultimately, keep this in mind. You stabilize a minus by pulling electrons away from it, away from that area. And that's what the fluorine is doing here. And this is an inductive effect. Through the single bonds, the fluorine is withdrawing electron density away from the oxygen nucleus, away from the anion. Now this one does not have the fluorine. In fact, all you can really mention is the sp3 carbon, and this is very important. An sp3 carbon is known to be electron donating by induction. And so I actually drew a donation this way towards the anion. And that does not stabilize the anion, that destabilizes it. And so over here we have inductive withdrawal stabilizes anion. Inductive withdrawal by the fluorine I actually already had that written, right? And thus there's less electron density on the oxygen. And if we can decrease electron density of the anion and make it more towards neutral, that's a stabilizing effect. And so this is more stable. Thus, this alcohol is more willing to act as an acid. It's the stronger acid. How about these two alcohols? Well, they're both sort of just plain hydrocarbon other than the OH. 1 carbon versus 2. We want to consider the conjugate bases. What's the difference in extra sp3 carbon? What does that sp3 carbon do electronically? Well, we wrote right here. An sp3 carbon donates by induction. This extra donation out here pushes towards the other way. Does that stabilize the anion or destabilize it? Well, it destabilizes it. If you have an anion, pushing electrons towards it makes it even more electron rich, even greater anion. We want to move towards neutral. This is not helping us move towards neutral, so this is actually a bad thing, making this the better one. Thus, this alcohol is more acidic than this alcohol. Inductive effects. This was inductive withdrawing, stabilizing this. This was inductive donation, destabilizing that one. Next examples, we got this ethanol, this branched here. That one is there. This one here. These two conjugate bases. That one has sort of one chain donating, one sp3 carbon donating towards this way. This one has 3. All 3 of these, that's an H there, all 3 of these methyl groups are donating into this carbon, and that is pushing electrons into this area as well. And so between these two, this one's more stable because that one is worse off. It's got three donators into this area, where this one only has one donator to the carbon that the oxygen is bonded to. That's worse off. That means this guy is more acidic because it's going to a more stable anion than where this one goes. Couple more. Which is more acidic, the alcohol with the F out here or the chlorine out here? Think about that for a second. And the next one, the difference is both with fluorines, but this one is further away from the OH group. 3 carbons between, this one only 2. Think about that one as well. Okay. Up here, this one's more acidic. And down here, that one is more acidic as well than that one. Well, conjugate bases. Which conjugate base is more stable? Both of these are halogens, and halogens are always going to be inductive withdrawers because they're electronegative. All right. But they're not the same. One withdraws more than the other. Fluorine is more electronegative, so this is actually a larger amount of withdrawing. That oxygen anion is most stable because the F is pulling more electron density away from the oxygen, getting it closer back to neutral compared to what this chlorine can do. Now down here, I've already got that conjugate base. The other conjugate base would be here. This versus this. Yes, the F pulls. Now if these were if the F was playing tug of war, it would pull just as much because the rope, no matter how long it is, the thing on the end of the rope gets pulled. But that analogy breaks down here, and what we can say here is as the fluorine gets removed from the area that we're considering, the effect, the electronic effect of this group diminishes. So it's further away, it's a diminished effect, and it doesn't pull as much. All right. And so if you had a compound where the F was way out here, boom, 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 something like this, the effect of this F just gets less and less and less on the electronegative, I'm sorry, on the electron density over here. Now in these examples I just had one halogen. It is very common to see 3 halogens. And of course if you see 3, well that's going to be a great effect. All these pulling. And even though this one is directly away, you got to remember this is tetrahedral. So these are not like 90 degrees to each other. All 3 of these are pulling away from the oxygen anion. And so if we had three fluorines on the second carbon, it would be more stable than if you just had one fluorine on the second carbon. Okay? I just point that out because you do sort of routinely see what's called a trifluoromethyl group in organic compounds, or chloro, or sometimes bromo, but the CF3 is actually a fairly common group. Okay, we'll see if any questions come up there. Those are some examples of inductive effects. Next is going to be resonance effects, number 3. Question: which compound is more acidic, the alcohol or the carboxylic acid? Now the name probably gives you the answer. This is called an acid because it is acidic. But let's explain why. Now of course we're looking at the OHs because the CHs are not as acidic. So which OH is more acidic? Let's look at the conjugate bases. Here's the conjugate base of ethanol. Here's the conjugate base of acetic acid, which by the way is known as what? Acetate. Now inductive effects will actually give you the right answer. We've got these sp3 carbons and these donate towards the anion. That's not going to stabilize it, that's going to hurt it. This sp3 carbon donates, but the oxygen here pulls away from the carbon that the group is on. And that would probably tell you that this is more stable anion. And since this is a more stable anion, you would predict that this is the stronger acid, and you would indeed be correct. But although induction may give the answer in this case, the more important reason is resonance delocalization. Now you can read what I have here. I'm going to give you a different take on it to begin with. Let's look at this. This is resonance, but let's look at it in this way. What is the hybridization of this oxygen here? Or actually, let's do it this way. We got a third lone pair. 2 lone pairs, now 3. The third lone pair is in what type of orbital? And the answer is sp3. Because this oxygen is sp3, and any lone pair there has to be in an sp3 orbital. I'm going to say the LPs in sp3 orbs. But what's the hybridization of this oxygen? And it is sp2. Why? Because the carbon next door is sp2 and it has a p orbital. And one of these lone pairs is in a p orbital. I'm going to say the new lone pair is. That's really not right. One of the original lone pairs was as well. But one of the lone pairs here is in a p orbital. And it's conjugated with the neighboring p orbital. Now see, both of these anions have these 3 lone pairs. Here, the 3 lone pairs are isolated. Okay? They're isolated. Over here, one of the lone pairs is conjugated. It is thus delocalized. And a delocalized lone pair is a more stable arrangement than an isolated lone pair. That's what makes this anion more stable than this anion. This is the most stable anion. And what we described here is resonance. Resonance is when, well, in this case, when the lone pair is conjugated with neighboring p orbitals. We have that here. We do not have that here. The neighboring atom, the neighboring carbon, has no p orbital. It's sp3. All right? That is the main reason, the overriding reason of why this is more stable than this conjugate base, and thus this is the stronger acid. Now, that really gives you the answer of resonance at this point. We can show some more resonance discussion. Whenever we do resonance structures here, we start moving electrons around. Pi electrons. Consider dipole. These electrons are pulled by this oxygen. We can actually move them up, take them and move them up on the oxygen, become the 3rd lone pair, and we can get this structure where the oxygen is now minus and the carbon is positive. We have a double-headed resonance arrow. This is a resonance structure because all we did is move pi electrons. Now, we can ask these electrons, or this oxygen, to share. These move in as a pi bond, create a pi bond here, and we can get to this structure. Now the carbon and this oxygen are both neutral. This looks like something we did when we were drawing Lewis structures. This carbon needs another bond. We can ask this oxygen to share. Now if we ask this oxygen to share and bring these down, we'd just be going back this way. But instead we ask this oxygen to share. And now we get 2 different structures here. And each of them only have a single charged atom. Now actually, what is the true structure of acetate? The true structure is a blend of all these structures, but these 2 contribute most. And that is if we drew this we had this positive here. I'm going to get rid of it. You had electrons here. Consider this here. If you had this situation, which oxygen would contribute electrons to this carbon? Well, they actually kind of both contribute because electrons like positives, and physics tells us that electrons are going to be attracted. But you can't draw a structure with double bonds to 2 oxygens because you break a golden rule. Carbon can't make 5 bonds. So do you just have 1 donate? If you only had 1 donate, we'd have double bond and we'd leave the other one as minus. Or we could have the other, and that's what I have drawn here and here. In real life, what's going on is they both donate, and it's sort of like this one kind of partially donates, and this one sort of partially donates, and you end up with something like this. And that's kind of the structure, but it's charged. Since this one only partially donated, there's still some partial minus left there, and this one only partially donated, so there's partial minus there. And this is actually the true structure of acetate. And you have two equivalent bonds here, but it's like a bond and a half. And this is called your resonance hybrid. Again, the actual true structure. But your resonance hybrids have these partial bonds, and they're a little cumbersome to think about, even though they're reality. Instead, we typically draw sort of incorrect structures and talk about how the true structure is a blend of these. But the important thing here is the charge has been delocalized. In this structure, the charge is on the oxygen, this oxygen. In this structure, the charge has been moved to the other oxygen. In real life, each oxygen has a partial minus. Which is more stable? Partial minus on each oxygen or a full minus on one oxygen? And the answer is partial on two different oxygens is better. And we say the charge is delocalized by resonance. And so that's another explanation of why resonance makes the acetate anion more stable compared to the alcohol anion or the alkoxide anion. Okay, I tried to give you some more here. Please read about resonance. Including in your textbook. You really need to get a good foundation of resonance from your textbook. Okay, let's skip over to hybridization effects. Number 4. Now here, as an example, I give you CH compounds. SPCH, SP2CH, and then all of these would be SP3CH. Now these are not that acidic, but of these three, which do you expect to be more acidic? And that would be the SPCH. More acidic than that, and that's more acidic than that. Why is this more acidic? Let's consider the conjugate base. Here. And then we'll show the one on the far right, the conjugate base here. All right. And this is more stable. Why? Well, they're both carbons, so it's not an electronegativity effect. Since they're both carbons, it's not a size difference. There's no resonance here. This is purely a hybridization effect. What type of orbital is this lone pair in? That lone pair is in an sp orbital. If you graph that carbanion, you should see it's in an sp orbital. This lone pair is in an sp3 orbital. This orbital is 50% s, and this orbital is 25% s. Which lone pair is more stable? Well, I'll give you the answer right here. This is. Because the lone pair is in a more stable orbital. Now, the reason it's more stable is because it's closer to the nucleus. More s character, the closer the electron can be to the nucleus because it has more s character. Where this lone pair is in an orbital that does not have as much s character, it thus has more p character, and as we know, a p orbital, there's actually a node at the nucleus where there is no electron density. So this lone pair is closer to the nucleus. Sometimes I'll say it's closer to mama. That's purely a hybridization effect. The lone pair is in a more stable orbital. Thus, the carbanion is more stable. Thus, this CH bond is more willing to be broken during an acid-base reaction than the other two. Okay, that is some discussion of acid-base chemistry up to here. What we've been looking at is determining relative acid strengths. That is, comparing one molecule to another and asking which is more acidic. For example, if you have multiple different potential acid protons in a molecule, asking which one is most acidic. So a relative comparison. Okay, there are some good warm-up questions that after going through this should hopefully be able to start answering. See if the material we covered makes sense. See if you can apply it. We also want to come back over here, but again, we don't have to judge what's the most acidic here. The strong acid is most acidic. You just know strong acids coming out of Gen Chem. Really what we have to look at is which atom is most basic. And that's what we'll start doing in the next video when we start looking at bases. Now this discussion will be much briefer because it will use the same effects we use for acids. We'll use these same effects, but we'll sort of reverse our thinking a bit. And I will explain what I mean. But again, we'll use the same 4 effects. So please make sure you sort of learn those before we move on. Okay guys, that's one of the first videos on acid-base chemistry, and we'll end there.